Okay, so welcome to the HPC Best Practices webinar series. The series is brought to you by the IDEAS Productivity Project, which is part of the Exascale Computing Project of the United States Department of Energy. The series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marcus from Lawrence Berkeley, Ashley Barker from Oak Ridge, and I will be the hosts for today's webinar, Reducing Technical Debt with Reproducible Containers, and the webinar will be presented by Tanu Malik. Tanu is an assistant professor in the School of Computing at DePaul University, where she directs the Data Systems and Optimization Lab. Her research interests span topics in data provenance, data systems, distributed systems, and cyber infrastructure for scientific data management. She received in computer science from the Johns Hopkins University and a National Science Foundation Career Award for her work on computational reproducibility. She's also a 2019 Better Scientific Software Fellow, as indicated in this slide you see. We have issued more than 107 tickets for this webinar, and all attendees have been muted by default. We'll be receiving questions through the Zoom chat and also the Google Doc. We have pasted these addresses in the Zoom chat. And the webinar will have breaks so the speaker can respond to the questions that come in. With that, Tanu, I'll stop my sharing here and you please take over.
Thank you, Osni. Let me share my screen. Osni, you can see my screen, right?
Yes, looks good.
Okay. Well, thank you so much, Osni, for the introduction, and it's a pleasure to be here virtually. Thanks so much for taking time out and tuning into this webinar. Osni provided a little bit of introduction. Let me just expand a little bit on that. My research experience and expertise is in databases and distributed computing. For the past 8 to 9 years, I've been working on data provenance, and more recently in using provenance for establishing computational reproducibility. I'm working on developing a system for efficient reproducible analysis. It's called Sciunit, can be accessible through this website, sciunit.run. And as part of the BSSW fellowship, I am very interested in reproducibility case studies in the high performance computing area, and especially how containers can be used for establishing reproducibility. I'm working on some problems these days, which is provenance alignment, trying to highlight sources of irreproducibility using provenance traces, and also determining how I can make Jupyter notebooks reproducible, which we all know they aren't. So that is about me, and today I am going to talk about reducing technical debt with reproducible containers. So let me demystify some of the words over here and this give a little outline for this talk. So first we are going to understand how technical debt impacts reproducibility and can we measure it. And in the second part of the talk, I'll be exploring this concept of reproducible containers and if they provide a mechanism to formally addressing the enormous problem. And finally, a guidance and summary. So part one, how technical debt affects reproducibility. So we are all familiar with monetary debt, especially on commodities such as the house, the car, the credit card. What is monetary debt? It is something that we are borrowing, a fixed amount of money that we are borrowing to purchase these commodities. Now, what does borrowing help us? Well, it helps us get this commodity faster or sooner, right? And so we like this fact that we can get this commodity sooner. Now, technical debt, which was introduced by Ward Cunningham in 1992, is no different. In science, the commodity is our scientific publication. And how do I get that publication faster or sooner? Well, one may say by being smart or putting in a lot of hard work, but increasingly by also borrowing from the scientific software that produces the publication. More publications, more borrowing, maybe not on the same software, but the overall research direction that a person is pursuing. And that results in, as the time goes, we are borrowing from and I'll describe what I mean by borrowing, but we are borrowing from the software for each particular journal deadline, resulting in technical debt. And in some senses, it's resulting in an overall poor scientific and research software that can be coming out from a given research group or a lab group. So what are we borrowing on? Well, we borrow on the quality of code, the design, environment debt, not keeping track of the environment, or documenting, or writing tests. These are dimensions of technical debt which are known to us. Now, going back to our analogy, if we do not repay our debt in any way, what happens to our commodity is that it is repossessed. So what should happen for a publication on which the technical debt that has been borrowed from the scientific software is not repaid? Well, increasingly, it is going to be marked irreproducible, which we know that if such a badge is given to a publication, it impacts citations and it impacts reputation. So people do want to avoid this badge. So let's go back to our dimensions of the technical debt and see that what we can do to address so that we do not get such badges. Now, as we can see, the characterization of the technical debt, such as poor quality, poor design, these are larger software engineering issues. And I won't be going much into them because they are actually very well referenced in the citation over here, but they do not impact reproducibility as such. So quality of design, poor quality of the code, design, or testing debt. I'm going to focus on environment debt and documentation debt, because these are two things that are immediately responsible for reproducibility. Okay, so this is the technical debt that I'm going to focus on, the environment debt and the documentation debt. But let's define, reproducibility. What do we mean by reproducibility? Specifically, computational reproducibility. So in this reproducibility, I'm not referring to bugs in software. We know that some of these bugs have led to catastrophes, but we are really concerned with this common case of irreproducibility, such as when claims in publications cannot be verified through available software. And in the worst case, they must be retracted back. Or when quick software evaluation is essential to trust the experiments, which are obviously being published in papers, such as an example over here that we are facing, the pandemic. There's a software which we know requires testing so that we can do our projections, the model projections correctly. In particular, let's relate these technical debt and reproducibility at a conference which is closer to home, the Supercomputing 2020, which is about to be held. So let's look at what is technical debt and what is reproducibility. What does it mean? I think we'll be better able to appreciate these two concepts rather than in a very abstract sense. So I was the artifact evaluation and description program committee member. This was done as part of the Transparency and Reproducibility Initiative in Supercomputing 2020. The idea is in artifact description and evaluation is that any paper that gets submitted must include an appendix with detailed artifact description of the environments and methodologies that were used to publish the key results in the paper. So when the authors submit these artifacts, the review process not only looks at the PDF document, it also looks at the artifacts that are being submitted. And the final rating for a paper is a combination of the technical review and the artifact review. Okay, so did technical debt affect reproducibility of claims? Let's see some results in this regard. So supercomputing had, as we can see at the bottom, 380 submissions, and each reviewer, like a person like me, got about 80 submissions to review. Yeah, a lot of submissions to review. And supercomputing had two phases for reviewing. In phase one, 75, as you can see, I have 5 over here, 75 basically got a rating of good and below. And anything reviewed as good was considered, or anything reviewed as good or below was considered unacceptable for submissions. So in the very first phase, authors have not submitted even the relevant artifacts for their paper. After revision in phase 2, 43 of them got approved based on their technical review and their artifact review for proceeding to phase 2. And after phase 2, 24 of them got a rating of very good and excellent from me. And the remaining of them, which is 17 of them, did not qualify. So that was a combination of technical review and AD&AE description review. One paper was considered unacceptable for artifact description and evaluation, and one of them was pushed for its excellent research idea, but it was considered unacceptable for artifact description and evaluation. In total, out of the 380 submissions, I'm told that 17 may be badged for, that is a final stamp of reproducibility will only be given to 17 of the 380 submitted submissions. So what does this say about the technical debt and reproducibility? What does these numbers say? Clearly, for most authors, in my experience, the reproducibility is an afterthought. And as you could see that after saying that a paper would not be accepted, which is like a stick, authors who had not taken this process seriously do submit. But even when they submit their artifacts, a big problem is identifying the files for an application. What are those files? They would miss, in many cases, they would miss what exactly consists of an application. They would lose out the data pre-processing steps. How was the data acquired? And how would this particular program lead to the result which is published in the paper? So the entire workflow is not there, even though some of the programs would have been submitted, a Zenodo directory would have been created, a GitHub repository would have been created. So clearly this is a time-consuming task. It did not happen in the phase 1, as we are seeing. Very few authors could submit it. And even in phase 2, it was a hard thing to get them to submit the complete workflow. And there was no mapping of experiments to content in the paper. And I would say it was not even that as a conference itself did not have the infrastructure to establish the verification of the final claims. And that is something that should be done. So I hope to have a better quantification of technical debt. This is the preliminary result, as I intend to co-chair ADA for next year's SC. But it brings us in this particular talk to talk about, is there a way by which we can reduce this author burden and the reviewer burden? And I want to talk about reproducible containers, if they can, in some ways, as I say, provide a formal start in addressing this reproducibility problem. So we have a reproducibility ecosystem of tools, such as Zenodo, GitHub, package managers, Figshare. They enable us to share data, share code. And we have also heard of the cloud sharing images, an entire virtual machine. We can share virtual machines on AWS or Azure. I want to specifically focus on Docker. As a container system, it has become very popular for doing reproducible research. So what do containers do? They provide a complete tool chain to simplify the use of containers. We can build containers, we can run containers, ship them, share them. And this BSSW itself, this IDEAS series, had an excellent talk a few weeks back on introducing containers over here. And just to be for the real people who are not very aware of what containers do, containers use namespaces. They will isolate everything in an application. So if an application, for instance, here using Tomcat, Java, and Debian distribution has to be run, then this application can run in isolation without interacting with the operating system kernel over here. Again, this container in green over here can operate in isolation without interacting with the operating system kernel or any other container over here. So in this way, a container behaves like a VM, a virtual machine, but is very much lightweight. It's not including the operating system. In addition, the containers can proportion the resources that are available to them, such as a CPU, memory. So for instance, the yellow container over here can use 20% of the CPU, a little bit of the file system, as much as is allocated, and some portion of the network bandwidth. And similarly, green can be allocated. So this is done through C groups. But most with everything with Docker containers, as we saw a little bit going back over here, you start with a Docker file over here. So the very first phase of building a container starts with a Docker file. This Docker file must be programmed. And as some samples show over here, where we are trying to build the applications, these can be pretty complex, like a regular program. So now let's think about, from a reproducibility perspective. It seems something paradoxical over here. If another software system must be programmed to achieve reproducibility, the question is, does Docker solve or create further technical debt? The technical debt that we have learned is when the user does not document the dependencies. And here we are aiming to achieve reproducibility by asking the same environment debt in the form of another program from the author. So it's to say that it is solving the reproducibility debt is only after you have learned what Docker does. So here is my claim. that declarative encapsulation of dependencies for isolated execution does not reduce technical debt. In other words, the containers in their current form do not reduce technical debt. The user must provide a complete description of what is required for an application to be able to even instantiate a container. So that brings us to further details of what a reproducible container can look like. Well, the very first thing it can do is automatic encapsulation of dependencies. And here I'm going to be going a little bit more into the details of the Sciunit system, which does this automatic encapsulation of dependencies. So the key idea in Sciunit is to identify dependencies during the program execution. So when your application is executing, it is accessing these dependencies. So why not at that very time copy them into some container-like environment? So Sciunit captures application dependencies during executions, and it also repeats executions within isolated environments with some guarantees. So why a guarantee? Well, if we go back to our Docker container example, a Docker file may change, and thus if it changes, its execution also changes. If we need a reproducible container, it must provide some guarantee that how close is a reviewer's execution to author's execution. So we need to map that those executions are exactly the same. So going a little bit into how Sciunit works, to capture or audit, Sciunit uses ptrace to observe the dependencies and environment variables. And it identifies binaries, libraries, scripts, and all the variables that the application is dependent upon. And these dependencies, which it is observing during runtime, are copied into a directory in the file system. So this is the host file system where the application is running. Inclusion of data files is optional. A user may or may not want to package based on the size of the data set, but I'll talk a little bit more as we go along in this talk. So if you look at the Sciunit file system slice, here we have an example over here. I have a weathersim.py, a Python program, which is inputting a file tokyo.dat, which is using that file. And obviously, since I'm going to be running it with Python, this file, when this process that will get instantiated, depends on the Python interpreter, which may depend on further libraries. So all of these are copied into the package, the reproducibility package, and its access log is also created over here with reads and writes, leading to a provenance graph. Now this created Sciunit log that I have and looking at how its actual graph is, we can identify what are the inputs, what are the outputs for an application. We can distinguish what are the system dependencies, what are the processes, and from that we can, and querying the repository packages that are there, the package repositories, we can create a Docker file for that given application automatically. And any content which was specific to the application can be identified that this is user content. This is not standardized system binaries that are available, and they can be copied directly into the container. Now, if you have automatically created this container, one can repeat it. It can be repeated by providing some guarantee, in which case the repetition takes place in namespace isolation, and each call is redirected within the package. So when this entire package is working in isolation, but for instance, when the user tries to access /user or tries to access a given dependency over here, well, it would be redirected back into that file system slice that we created. Now, how exactly do we do the matching between the two logs of the audit and the repeat? We provide some guarantees that whether the execution is exactly the same. We use Merkle trees and these provenance logs, but I will not go into detail on them. So to come back, Sciunit takes 3 steps to create a Sciunit. When you are creating, it's independent of any programming languages. These are all the various kinds of programming languages with which we have tested with. You share it, and currently it can be shared on Figshare and HydroShare, which is popularly used by geoscientists. And then once you have the package, you can repeat it on any of the cloud environments or research cloud environments. The current limitation is that you can repeat it on any Linux machine, not Mac OS X or Windows. Any Linux distribution, any Linux machine with a kernel distribution in which glibc is greater than 2.17, and Python should be greater than 2.7, which is standard basically standard in all environments. So that in some senses enforces the reproducibility. We have to ensure the reproducibility of Sciunit itself, and by reducing our dependencies over there, we ensure that. Now, in high performance computing, we need network-enabled Sciunit. A network-enabled Sciunit traces the application on the leader node and each of the follower nodes, and it audits both content and messages. That's a lot, but yeah, it audits both content and messages, and which are executed between the master node and the leader node and the follower node. And currently, the audits are merged manually. What I mean is that the audit, which is on each independent nodes, is brought to the leader node, where we merge the network exchanges between the so the step of just bringing the audited content is manual. Now, one may think about that, how does Sciunit differ from recording of messages in MPI applications and the deterministic replay that systems like REMP do? So here, again, as I mentioned, the Sciunit records messages, but also contents. And that is really important if you want to do reproducibility of applications on different machines. And machines may differ because of heterogeneity, the specific libraries that they are using. When you repeat, there are 2 execution modes. You can repeat in an offline mode. So the idea is that it might not be possible for a person to have the same setup. So you can just repeat it exactly in an offline mode at one single node without having any connection to other nodes, or when you have exactly same number of nodes, in which case Sciunit needs to be configured for the host names and IP addresses. So that is Sciunit. Let's look at how Sciunit behaves on some of the programs that we have tested. So these are real applications. The first one, FIE, is a food inspection evaluation. It's a data mining data science, I would say, application which uses random forests to predict where food violations would be happening. Variable infiltration capacity, VIC, over here is a data pre-processing pipeline for a computational hydrology computational model. And intermittent query engine over here is a database application, which is using a Python application and SQLite, which is embedded in Python 3 to do database style querying in the Python application. So as you can see, the source code languages are of a variety over here. The applications are of modest sizes with some runtime, and these are analysis applications which a user might be doing with a lot of with some data. So let's look at the difference between Sciunit and Docker. So for the very first thing, let's look at the sizes of Sciunit and Docker. So the first bar over here is the application size. For IQE and FIE, as you can see, it's 306 megabytes, something 1.2 gigabytes over here for WIC. And as we can see, the Docker sizes are fairly large, about 8 to 9 times larger than the application. Sorry, I would say is hard. So the Docker sizes are almost double. In this particular case, is almost double, and over here, as we can see, is about 8 to 9 times in case of FIE, about 8 to 9 times larger. But as you see, the Sciunit size is much smaller. Now, Sciunit internally uses block level deduplication, which makes Sciunit size even lower than the original application. So if you look at the middle bar over here, it's lower. And so it's identifying duplicate data at the block level, even within an application. So the Sciunit sizes are much smaller because it is only including the necessary and sufficient files for an application. So if you're running an application which does not need the base images or any such other paraphernalia of a Docker container, well, Sciunit is a lot more efficient to use than a Docker container. What about execution and re-execution? So the normal runtimes for an application like IQE is very small, like 5 seconds. For FIE, it's as I said, is a data science application running a random forest. It's fairly 287 seconds. For WIC, it's data intensive but not compute intensive, so it's about 40 seconds. So for here, we are including the Docker build time because you'll have to download the container as a one time even, but you'll have to download it, and that time is sufficient, is a lot over here. So 191 seconds is the Docker build time that I have over here. 1235 is the about 1200 seconds to just build this Docker container. But if you look at the Sciunit times, are fairly close to the application normal runtime. Little bit overhead that we are seeing is because of intercepting and as well as copying the data. So audit time is more than the execution time, but execution times are very close to the normal run times. The Docker build time, the Docker execution time, we are seeing increase in that, and that is coming not because of the execution of the application, but because we have a layering of the file system, and because of the layering of the file system, especially in case of FIE, which is running this random forest on a large number of City of Chicago data sets, there is, because of the layering, we are having a little overhead in FIE. What about the network execution, the network-enabled Sciunit? So we ran it, the results are not on a very large science use case that we have, but we have run it on a NASA parallel benchmark with Class A applications and Class B, each of which are exchanging a modest amount of data, like a very small amount of data, 524 kilobytes and 268 kilobytes. So we have just a 3 machine set up right now. The idea is that they are pretty much compute intensive. We are trying to determine what is the just the heterogeneity of the machines, and can we capture everything from the machines. And as we can see, the normal execution time, there is about 2.1% overhead for auditing the content as well as the logs. Auditing the logs is 2.1% overhead, which is including the network messages that we are logging. But the content audit obviously is larger because we have to now copy the file. So about 5.3% overhead over here. So for the specific class B over here, that we have the overheads actually reduced for the metadata audit as well as for the content audit. But again, the amount of data that is being exchanged is also smaller. WIC, which can also be run in parallel mode, we have try to look at, the amount of content overhead for a real application does go significantly, and one can look into how one can avoid copying some of the messages, some of the content which might be already be present, such as in an MPI application, it would be the same program that would be running at multiple nodes, and one doesn't need to audit them again and again. So those are the performance results of Sciunit. Here is a slide for the sample interaction with Sciunit, which is very Git-like. Here I am creating a Sciunit, just like you open a Git repo. You might have an application. This is the start point of the application. Is inputting some parameters, such as a data set, and all you need to do is Sciunit exec. And then you would do a Sciunit list. So you're actually auditing the application while it is executing. As we can see, you can list whatever you have, the packages that you have created. You can show details about them over here, and you can push them onto some other host machine. For instance, this could be running on Alice's computer, and Bob might want to use it. So once you push it, it will be stored temporarily on our cloud server. You'll get a hash ID, and then on the other machine, you can just open with that hash ID, and then just list your Sciunit, repeat the execution. This is the first execution that is there. Or you may change the execution. You may say that, well, I want to run with a different data set. Instead of my 2017 data set, I want to run it with 2018 data set. Run it, and then you'll have two executions that would have been captured. Again, Sciunit is using deduplication inside, so it is not that the FIE application is being captured twice, it's only being captured once. So I spoke about this automatically creating this reproducible container to reduce the technical debt. But what about data, right? So we have lots of data. Right now, the way I showed you, all the data is captured. So it's a binary sort of decision that you either include all the data or you do not include. But can we do better? Can we actually have a reproducible container which is only using the necessary and sufficient amount of data that an application uses? So we consider this term debloating the container. Sorry.
Is it a good time for questions, or we have some questions here? Or would you?
Sure. Yes, definitely. Yes, anytime. Yes.
Okay, before you get into this.
Yes.
So going back some slides, on your description of tested languages, I noticed that CUDA wasn't present. Does this work with CUDA compiled, PyTorch, TensorFlow, etc.?
So with CUDA, audit happens, repeat, you can repeat in a Docker container, but audit will happen. You would have all the necessary dependencies. Repeat, as I'm saying, that we are guaranteeing the specific repeat that requires us to look into the system call architecture of GPUs. Not all the system calls that we support right now are being mapped into the GPU system call architecture.
Okay, another question here. Who pays down the technical debt of the Sciunit system itself?
Well, we are taking the debt for, thankfully, NSF has been funding us, so we are taking the technical debt of Sciunit system and keeping it up to date so that it can support multiple environments.
So another one here, does Sciunit work similarly with the singularity?
Yes.
All right. So and then final one, I think, is for now. Is there a Sciunit to Docker converter? I would imagine for wider deployment that might be useful.
Yes. This over here, we recently published this paper about a Sciunit to Docker. So we have tested this on about 40 Zenodo projects. We haven't publicly widely released it. There is still more testing that is required for different, as you said, as we said, we support a variety of programming languages over here. We have to test it for that as our Docker component also. It's very much in demand, I must say. And before really, we haven't publicly released it for that very reason.
Okay, please continue, Dinesh. Tanvi, that's all we have for now.
Okay, so thank you, Osni, and thank you for the questions. So let's go to the second topic about is it possible to reduce the container size, which is should we include data in it or not? And so we are looking into this concept of that the container, especially for a reproducibility perspective, may not need to include data which was thought that the application would be using, but maybe the application does not use it. So if the application does not use it, the container is being unnecessarily being fattened or bloated, and we can figure out whether what is the necessary amount of data that is required for that container. So let's say we have, just to motivate this idea, let's say we have a simple program that opens this file over here, test.txt, and it is seeking to byte position 100, and it is reading C number of bytes. And let's say this program was run such that it every time it is run, it is reading from 100 to 150 or 100 to 190. So we have this information that these are the possible executions of this application. So now the question becomes that should we include test.txt or should we include just test.txt from offset 100 to 450? I mean, technically one should only be including 100 to 100 looking at the specific ranges exactly where it is reading. But here, as we can see that we don't know, and we might just include 100 to 100 to 450. Because that is what the application uses. So MIDAS is that tool minimizing data sets. It is automatically identifying and including only the relevant data chunks and mapping these high-level user inputs to file offsets. So how does it do it? It uses partial evaluation, which is an compiler optimization technique to prune code bases. And partial evaluation typically uses static inputs to generate a specialized version of the program that only accepts dynamic inputs. So let's look at a very quick example over here. So for instance, we had this program which is computing this function, compute opposite. And compute opposite, as we can see, is taking an input float angle, and one is computing the tan of the angle input of the function. So the tan function would require the math library to be included as part of this container. Now, if I look at the program, the value of that would be passed to this function, which is angle, is already present over here, which is pi by 4. So what the specialization through partial evaluation does is it identifies that the red thing with the viewing angle is a static input, and it creates a specialized code where the value of the tan of angle is already present. So you don't need now the math library, and so your code base is essentially pruned. So we are adapting this idea to IO specialization, and the idea is to again instrument your code and find what particular data chunks I need to extract, and either include them with the binary or have a little database which can include these set of chunks to be able to run in the container. So basically the idea is when the program will do a read IO call, then instead of the read IO call, well, there would be a mem copy and it would be reading from the actual chunk. So the actual chunk is being copied over here. So you copy from the global variable to the read buffer, and you update all the IO call variables, and basically the application uses the data from that buffer. So we are specifically looking at how this can be helpful for specializing the IO calls in scientific libraries. Some of the scientific libraries, such as NetCDF and HDF5, they have a lot of data, but a few variables that are accessed by an application. So here, for instance, we had a larger file, which was about 30 MB, and the application was only accessing the temperature attribute. So we determined that, well, only 6.6 megabytes from that 30 megabytes were actually used. And we looked at different sizes of the files, and we could determine, hey, what exactly is the amount of data that is being accessed from the temperature attribute. And then one can do the application may give a spatial region. And so the amount of data that is actually used is much smaller. So that brings us, so MIDAS is still work in progress. One may say that, well, the inputs, exactly kind of baking the data into an application is dangerous, because what if the application uses some other input, some other data? And that is part of our the research agenda that we have. Partial evaluation can help us determine other variants. Given these inputs, we can determine some other possibilities that can exist, and basically include that much amount of data, but not any data that was never ever touched by an application. So allowing for adjustable inputs, especially during sensitivity analysis that one is doing, is part of what we are thinking, how to improve partial evaluation. So any questions on this part?
We are good.
Okay, so this brings me to the final part of this talk. So what I have mentioned is technical debt affects the reproducibility of scientific claims. And what we saw was that this process of evaluating scientific claims is itself being rethought. Artifact description and evaluation is becoming part of our conferences. And we need better reliability. Obviously, authors do submit a lot of many files, but we need better mechanisms that can give us quick verification, a quick validation that this program would produce the result that is mentioned in the papers. Containers will be a prominent choice, but their reliability is poor. As we are seeing, dependencies must be specified. They are inefficient to use space-wise, and there are no guarantees that it can provide for execution verification. And for interactive programs, which Sciunit works very well, I mean, Docker is very difficult to work with respect to interactive programs. So these methods of Sciunit and MIDAS are interesting in that regard. I would strongly encourage you guys to use Sciunit for your next paper submission. We have it downloaded about 850 times. There are 8 active contributors to the project. pretty much my students. Some other students from other groups back in India and over here in the US came across the project and have been contributing. It's actively used in geoscience applications, disciplines. We have had it in space science, in hydrology, in solid earth, and yeah, in these three disciplines, there have been laboratories in the US who have used these and actually educated their graduate students to use this as a common tool while they are doing their work. So you can download it from sciunit.run. If you have any issues, you can email us.
There is a question here that just came in, if I may. So
yeah.
How do you deal with host CPU system dependent system calls, such as AVX 512 intrinsics, MKL presence or absence, etc.?
Actually, Osni, can you repeat the question? I'm in my office and the train is going, so I couldn't hear it well.
How do you deal with host CPU system dependent system calls, such as AVX 512 intrinsics, MKL presence, or absence, etc.?
Yes, so these are specialized system calls. In one of our papers, we document, we audit about 55 system calls. These are pretty much the system calls that are in the Linux kernel distribution that have been documented, and they are for different architectures. They are for the x86 ABI interface that is there. We are only doing it for that specific architecture. If we have to do it for the specific system calls that you're saying, the question is that we'll have to have developed ptrace which can actually look into this specific system calls and then be able to audit. I hope that answers that. Osni, are we good?
Please go on, Shu. There, please go.
Okay. So coming back to is there a final thought over here, a final sort of summary, which is there a guidance for improving reproducibility? So I would like to sort of say that, reproducibility is both a process as well as a guarantee. So we, as an author, we see it as a process which is of increasingly difficult levels, I would say. You want first the program to run, but once you have gone from these blue and green bars, you want to run it with different input parameters. You might want to change some part of the program, or you might just want to make it available, which requires a lot of documentation if you are making it widely available, which is publishability. So it's a process. It's a process which has to be undertaken, and it has different levels. So it cannot be said that reproducibility is only one thing. No, it's at multiple levels. And we require guarantees on this process at also guarantees at this for this particular process at these different levels. It cannot be that we just say that an application is reproducible and that's it. No, it might be that it runs, but it does not produce the same result, or it produces a nearby result. So we need different levels of badging as well, which ACM is already doing, to say, well, we could run the application, we could find all the artifacts, but we could not run it. So different kinds that we could change the method and so on and so forth. So it's both a process and a guarantee. What we need from a technical debt perspective is that we need to identify what are our sources of irreproducibility. So technical debt is, it's a broad software engineering term. We have to identify what part of technical debt applies to the region of or applies to the area of reproducibility. And for that, according to me, we have to start from identifying what are our sources of irreproducibility. And they can be multiple, like they can be concurrency, hardware. It could be that the application is using random, just using some randomness, which might be dependent on some random libraries which are providing that pseudo randomness. Or it could be application complexity, the way we are seeing, having a lot of different kinds of programs that might be based on which an application is composed of, or just the state of the application. What exactly is it doing from one iteration to the other iteration? Or it might not be, the reproducibility might not be because of the application, it could be because of bugs outside the application. So what can we do over here? Well, as we're seeing, concurrency and hardware are still harder things. They aren't sort of tools which, there are definitely lot of ideas within deterministic replay and record and replay in these areas, but there aren't tools which give you reproducibility easily. With Sciunit, we are seeing that there is things that can be done with respect to algorithmic randomness. We can identify that your application is using a library which is itself dependent upon accessing the RAND system call. So we can identify things like that. We can identify application complexity, how complex it is. We can also do execution state, determine what is the execution state at different points by doing checkpointing, and that's additions that we are doing to Sciunit, that we can capture that state as well. And by applying isolation, doing this within the namespaced environment, we are avoiding bugs outside the application. What is still remaining is being able to identify reproducibility within irreproducibility that might be coming due to concurrency. The basis for all this is definitely, we collect as much of data as possible. Metadata, provenance, the snapshots, that's very important that we collect the snapshots, because unless we have the content, we cannot replay it exactly. We do not know that it is exactly matching to the previous state. And finally, we need methods for analyzing the metadata. So I think that for improving reproducibility, we need a system which can, gives us this ability to provide us isolation to begin with. But after isolation, it has the necessary amount of metadata which can be analyzed, and some kind of guarantee can be given, which can lead to a badging or wider claim for reproducibility. So I would like to end over here. I would like to acknowledge the students and research engineers who have worked with me, the postdoc Hai, who worked with me on this project, and acknowledge my collaborators. They have been very helpful in giving us use cases, as well as in helping us tell us that what is the right interface from which a student, with which students as well as experienced researchers can feel comfortable with in learning about reproducibility. And finally, my funders, National Science Foundation, the BSSW program, the Bloomberg Foundation, NASA, and DePaul. So with that, I open for questions.
Thank you, Tanu. We have a couple of questions here. Perhaps, let's see. How does Sciunit handle interfacing with fabric libraries, verbs on various machines for MPI applications, which are typically installed and managed by the system, by the site systems administrators?
So Sciunit works in the user space. If your application is using it, then it would be able to identify that library and would be able to copy it. So it doesn't require any root permissions over here. As long as your application, if your application can run successfully, Sciunit can also will also capture those dependencies.
Another question here. Singularity MPI applications can scale to hundreds or thousands of nodes at near the same timing as bare metal. Can one do the same with an MPI application that's packaged with a Sciunit?
Yeah, that's an experiment that we still have. I cannot, I don't see why it wouldn't be able to do it, but that is still an experiment that we have to do to show that scalability.
Okay, Anshu, I think that's, Tanu, sorry. Tanu, I think this is the last question we had. Thank you very much. Thank you all for joining us today. I'd like to share my screen here to announce the next webinar in our
I can stop sharing this
series.
Yes.
So thank you all again for participating. We wanted to improve the series, so please feel free to give us feedback. There is this survey that we have put together. The slides and the record will be available at these two sites next week or early next week. And the next webinar in this series is going to be on December the 9th. It's the last one in 2020. Software design for longevity with the performance portability. And it's going to be presented by Anshu Dubey from Argonne National Laboratory in the University of Chicago. And we have already a web page for it, and people can already sign up for this webinar. So thank you all again for participating. Ashley, would you have some final remarks? Thank you, Tanu.
Thanks so much, Osni. Yes.
Yep, that's all I was going to say is thank you to Tanu, and great talk, and I hope everyone has a great week. Thank you.
Thank you. Bye-bye.